Now Heisenberg uncertainty principle. Now according to Heisenberg's uncertainty principle, for any particle like electron, proton, which are microscopic particles, right? So for these type of particles, it is not possible to locate its position exactly as well as to find its finite momentum. Means position and momentum both simultaneously cannot be exactly decided. There is uncertainty in position if momentum is finite, and if position is finite or fixed, then momentum is uncertain, right? This is Heisenberg's uncertainty principle. Suppose in position, the uncertainty, that is delta x, and in momentum the uncertainty, that is delta p. Then the product of delta x and delta p, that is equal to h upon 2 pi, that is also represented by h cut. Okay, so here say, suppose we take in this particular equation delta x, that is equal to 0, means the equation that is delta p equal to h cut upon delta x, and in that equation if we take delta x equal to 0, when delta x is 0, delta x represent the uncertainty in the position. If uncertainty in the position is 0, it implies that now position is fixed one. So in equation delta p equal to h cut upon delta x, if we substitute delta x equal to 0, then h cut upon 0, anything upon 0, that is infinite. Clear? It implies that momentum, that becomes uncertain. Uncertainty in the momentum, that comes to infinite. Means momentum is not finite one. Similarly, if we take delta x equal to h cut upon delta p, then in that, if we substitute delta p, that is equal to 0, means uncertainty in the momentum, that is 0, means momentum is finite one. Then uncertainty in the position, that becomes infinite. So simultaneously the position and momentum, that we can't measure for the particle. Okay, now see here, if the particle behave as a wave, at that time actually what happens, suppose we consider the wavelength of that particular particle, it implies that when it behave as a matter wave. So that particular wave, which one is the representative of the particle, for that the wavelength lambda is suppose fixed one. Then as per the Broglie's equation, lambda equal to h upon p. So p, that is h upon lambda. It lambda, that is fixed one, finite one, then p, that is also finite one, right? As per this equation, p equal to h by lambda. But any wave with wavelength lambda, that can propagate up to infinity, or in other words we can say its activity, that is up to infinity. So when we say this particular wave is the representative of particle, but that wave move from minus infinity to plus infinity, then what is the position of the particle? That we can't locate. Clear? So here if we want to locate the position of the particle, then we have to restrict the activity of that particular wave, which one is the representative of that particle. So scientists introduced the concept of wave packet. Wave packet means what? Wave packet, that is nothing but the resultant wave, which one is made by superposition of number of waves with different wavelengths. So here the concept is this one: when the particle behave as a wave at the time, that matter wave, that is the combination of number of wavelengths. So when number of wavelengths superpose, then for the resultant wave obtained due to superposition, its activity that will be restricted in the finite region. So in the finite region, we will get, see in the figure, the amplitude of the resultant wave, that is maximum one, and where the amplitude is maximum, there the probability of the particle to be, that is maximum one. That is maximum one. So in this way we can fix the position of the particle. But if the position is fixed, then as per equation P equal to h by lambda, but lambda, that is the combination of so many wavelengths. So here, if we consider all these wavelengths, then momentum becomes uncertain one. Clear? So this one is Heisenberg's uncertainty principle. The position and the momentum of the particle can't be measured simultaneously. If any one of this one is finite one, fixed one, then other will be uncertain one. Clear to all of you? Example 11.4. What is the Broglie wavelength associated with an electron moving with a speed of 5.4 into 10 raised to 6 meter per second, and B, a ball of mass 150 gram traveling at 30 meter per second. Now see, first for electron, mass of electron, that is 9.1 into 10 raised to minus 31 kilogram. Speed of electron, that is given to you 5.4 into 10 raised to 6 meter per second. The Broglie wavelength, lambda E, that is h upon Pe, wavelength of electron, momentum of electron. So h upon mass of electron, speed of electron. Now substitute the value of h, me, ve here, and then solve it. You will get wavelength of electron. Then for ball, mass of ball, that is 0.15 kilogram, speed, that is 30 meter per second. So wavelength, that is h upon Pb. So h upon mass of ball, speed of ball. Substitute again the values of h, mass of ball, and speed of ball, and then solve it. You will get the wavelength of ball. Clear to all of you? Example 11.5. An electron, an alpha particle, and proton have the same kinetic energy. Which of these particles has the shortest, the Broglie wavelength? Now see, we have the equation lambda, that is h by p. Here it is given to you, all these three particles have same kinetic energy. Okay, it implies that now we have to introduce kinetic energy in this equation. So we know this thing, kinetic energy, that is p square by 2m, therefore p equal to under root 2mk. So here p is replaced by under root 2mk. Now kinetic energy, that is same one for all these three particles, that is given to you in the question. H is constant, 2 is constant. It implies that lambda proportional to 1 upon root m. Okay, so the particle which one is with maximum mass, the wavelength of it, that will be minimum one. So minimum, the Broglie wavelength, that will be of alpha particle, because mass of alpha particle, that is maximum. Clear? Next, example 11.6. A particle is moving 3 times as faster as an electron. The ratio of the Broglie wavelength of the particle to that of the electron is 1.813 into 10 raised to minus 4. Calculate the particle's mass and identify the particle. See, we have lambda, that is h by p. P, the momentum, that is mv, so h upon mv. So lambda of electron, that is h upon mass of electron, speed of electron. Lambda for particle, that is h upon mass of particle, speed of particle. So lambda e upon lambda p. So if we take the ratio of these two equations, we will get resultantly mp vp upon me ve. So mp upon me, that is equal to lambda e by lambda p into ve upon vp. Make mass of particle mp as a subject. So mp, that is equal to me into lambda e by lambda p into ve by vp. Now here, see, the ratio of the Broglie wavelength of the particle to that of electron is this one. So in this equation, when you substitute here this ratio, that is lambda p upon lambda e, particle to the electron given to you, and in equation it appears lambda e by lambda p. So when you substitute this one as 1 upon 1.813 into 10 raised to minus 4. And then here, say the particle is moving 3 times fast than electron. So speed of particle, that is 3 times the speed of electron. Substitute that, and then substitute mass of electron, solve it, and you will get the answer 1.675 into 10 raised to minus 27 kilogram. And this one is mass of proton. It implies that that particular particle, that is proton. Clear to all of you? Next one, example 11.7. What is the Broglie wavelength associated with an electron accelerated through a potential difference of 100 volt? Now V equal to 100 volt, lambda, that is 1.227 upon root V. Now here, substitute simply V equal to 100. You will get 1.227 upon 10. Your answer will be in nanometer. Theory માં આપણે આ equation લખેલું છે. So your answer, that is 0.1227 nanometer. Clear to all of you? Very